In this lesson, we'll look at ionization in more detail. We know that alpha and beta particles ionize air atoms by knocking electrons off them. These are the electrons in the shells that we've talked about before. This is a different shell, and this tiny thing in the middle is the nucleus. These aren't to scale. These electrons would be far smaller than we could see. So look what happens when we pass some low energy alpha towards the atom. You can see that the electrons are far away from the nucleus, which has this positive charge here. So when we fire an alpha particle at it, that causes it to be ionized, this atom to be ionized, and the electron travels off with the alpha particle. If we try that with a high energy alpha particle, you can see that it takes, it's going too fast, causes a bit of a hiccup here, but because it's going too fast, it doesn't spend long in the vicinity of this electron and doesn't cause it to break away. We can see this in what's called a cloud chamber. In a cloud chamber, you have alcohol vapor, and that will condense into tiny droplets around each of the ions. So when you've taken an atom, you've ionized it, you'll end up with tiny droplets around each ion. And millions of these droplets make the little clouds that you can see. And alpha particles have a big mass and a charge of +2. The positive charge means they cause lots of ionization in a very short distance. Each time the alpha particle rips an electron off a molecule, it loses some of its own energy and it will slow down a bit. And an alpha particle might make 100,000 ionizations before it loses all of its energy. It grabs 2 electrons and becomes a helium atom. So although some of those electrons are ripped off from the outer shells of the atoms, not all of them would be connected to the alpha particle. But once the alpha particle has grabbed 2 electrons, it's going to become a helium atom. And this is why the cloud chamber trails for an alpha particle are short and fat. An alpha particle will ionize most air molecules it passes close to, which is why it loses its energy so quickly and has a short range in air. Sorry, I'm jumping about a bit. And it's why the trails are short and fat. We fire low energy. Okay, again, here's a low energy alpha. The alpha particle has a big mass, so it's difficult to change direction. And that is why the path in the cloud chamber for the alpha particle tends to be quite straight. You may notice that the paths start very thin and then get fatter. This is because the alpha is more ionizing when it's going slower. If we fire high energy alphas, you can see that the low energy alpha spent more time near the atom, so it has more chance to ionize it. With that high energy alpha particle, it caused this little electron to sort of burp a bit, but it couldn't actually ionize it, this atom completely. So we're now going to see what happens when we connect the high energy alpha. So here we're connecting the high energy alpha. and it's saying that this would also produce low energy beta as well, but this isn't showing this effect. So you'd actually get some beta trails as well. Notice that ionizations are much further apart. So if we change this to fire some beta, here we go again. The beta's single negative charge means it ionizes, say, every 100 or so air molecules it comes across. If the chamber was very big, then the high energy betas would eventually follow paths like this as they came to a stop. So here's a low energy beta. And you can see that the beta's path is deflected, and that's why the cloud chamber shows a zigzag path. The tracks made by the low energy beta are thicker than for high energy beta. So if we try the high energy beta, if we look at those ones, change it for the high energy beta. Sorry. Well, at least you saw one there. We need to hold it here. Must be a right way to click this in. That was worth waiting for. So you can see these high energy beta tracks, much thinner, they're dotted. You can see it travels distances before it ionizes any of the atoms it comes into contact with. Again, this is because the beta particle is more ionizing and it's going slower, since it spends more time in each air molecule. With low energy beta, the paths are different lengths. This is because beta particles from the same source come with a range of energies. So unlike the alpha, where they all tended to be the same energy, so they all travelled about the same time, same distance, in the cloud chamber, the beta particles can be very short or very long. And it's the ones that have higher energies, as you'd expect, travel further. A beta particle and alpha particle of the same energy will make about the same total number of ionizations before stopping. But the alpha particle causes those ionizations in a shorter distance than the beta. And that's why an alpha particle has a shorter range in air than a beta particle. Let's see what happens when we drag the gamma source into place. Gamma is only emitted as a result of alpha or beta radiation, but we use a lead plug as a filter so that the gamma can get through. Obviously a lead plug would prevent the higher alpha and prevent the beta getting through, so it's filtered. In a cloud chamber, the single gamma ionization tends to happen in the wall or the floor of the chamber rather than in the air. So they were low energy gamma. These are high energy gamma. The gamma hits the walls, knocks out an electron, and it travels in all random direction. And if you think about it, the electron is going to leave a track like a beta particle. Alpha, beta and gamma radiation all cause ionization, and the ionization can be detected to show that radiation is present. And we can use that, a Geiger-Müller tube, to show that. Inside a Geiger-Müller tube, the ionization will cause more ionizations, and that can then be detected by a current.